So what we've got here is an electric fan, this little electric motor here, that's got its two wires connected to a thermocouple. There's no battery or anything like that, so there's no source of electrical energy to make this thing go. We've got one wire connected to a piece of metal that is in ice, and then we're going to put steaming hot water at near 100 degrees C connected to the other wire, the other piece of metal connected to the other wire. So there's a big temperature difference between these two wires, and just connected on these plates, one at about 100 C, one at about 0 C. And as we know from our studies of the laws of thermodynamics, thermal energy wants to go from hot to cold. Right? Things never go from cold to hot. This isn't going to get colder and make the hot water hotter. It's going to go this way. Both of these things want to try to end up at the same temperature. So the thermal energy is moving right now from the hot water through this piece of metal connected to this other piece of metal into the cold water. And that thermal difference is at the basis of so much of what is involved with thermoelectric power plants. With our utility scale power plants, we've got to have a very hot source of thermal energy and a cold source on the other side of the power plant so that we can actually extract mechanical energy from it. And we're going to see that happen here. Instead of using this hot water to make steam to turn a turbine, the flow of thermal energy through here is going to cause electricity to flow through the wires that are connected to this fan, and we will see the fan motor start going. In fact, I saw it inch a little bit like it wanted to move. We'll see it go, so it wants to move. It's getting very close. So we're just heating up this piece of metal and cooling down this piece of metal, and once that temperature difference gets enough, then this thing will start spinning. Oh, I can feel it wants to go. Yeah. So, as you know, for power plants, the efficiency of the power plant is fundamentally limited by the temperature difference between the hot side and the cold side, and sure they're in good contact with each other. And the greater that temperature difference, the greater the efficiency that we can have. And so on Earth, we are limited on the cold side by just how cold the environment is. And so to get a very efficient thermoelectric power plant, we need to have a very high temperature on the hot side because we can't really have anything colder than about whatever our ambient environmental temperatures are on the cold side. You can have a power plant running with a small temperature difference, but then it's going to run at a very low efficiency. Oh, it's so close, but not yet going. I think it'd be better if there was.
Just need a little nudge.
I did touch it again because I could sense that it was getting close to the end, but obviously I didn't give it enough of a spin to make it take off like that. So now we're seeing the electric motor turning the fan. Where is that electricity coming from? There's no battery or other source of electrical power here. That is coming from the flow of thermal energy from the hot side to the cold side through a thermocouple here in the middle where our wire is connected. And as the thermal energy is flowing through here, it is causing electricity in the form of electrons to flow through this electric circuit and cause that fan to go. So the source of the energy is the thermal energy in the hot water here. As that energy is going over to the cold side, being conducted over to the cold side, we are stealing some of that thermal energy and converting it into useful or mechanical energy. And eventually, as that's happening, this is cooling off. And as it cools off, we've got less thermal energy available. And eventually, if we waited long enough, this would cool off far enough, this would warm up enough, there wouldn't be a temperature difference anymore, and there would be no more flow of energy, and the fan would stop. we would have extracted some of the thermal energy from the hot water to make the fan run. The rest of the thermal energy would have just gone into warming up the ice on the other side. And that's in some ways very similar to what happens with utility scale power plants. We extract some of the thermal energy from the steam that we make by burning coal or oil or using radioactive materials, and we cause a generator to turn, and the rest of that thermal energy goes into heating up giant cooling towers of water, which we see evaporating steam, and that warm water is then dumped back into the environment. And now we've lost enough of our temperature difference there. We've extracted as much mechanical energy from the system